Welcome back, guys. We are now moving on to Chapter 3, Composition of Substances and Solutions. So this chapter has only 4 sections, but they're very important sections to understand and comprehend. So we'll be going through a good amount of examples and make sure that you follow along and that you do them yourself to make sure that you truly do understand what is being taught. So just to kind of open up with a bit of an example, talking about mixtures and solutions, we're going to talk about a little later in the chapter. A swimming pool is an example of a complex mixture, because you've got a lot of things that you have to maintain. You have to make sure you have the right chlorine level and pH and lots of things to keep it safe and also keep it clean. So we're going to start with 3.1, formula mass and the mole concept. So in this, we're going to calculate formula masses for covalent and ionic compounds and define the amount unit mole and the related quantity Avogadro's number to explain the relation between mass, moles, and numbers of atoms or molecules and perform calculations deriving these quantities from one another. So let's start by talking about formula mass. The formula mass of a substance is the sum of the average atomic masses of all the atoms in the substance's formula. So literally you look at how many of each atom there are, you look at its atomic mass, you add them all together. A couple things to note, covalent substances exist as discrete molecules. So a water molecule is hanging out by itself, so they're individual molecules. If you have a thing of water, you have a bunch of H2Os hanging out. So the formula mass of a covalent substance can be called its molecular mass. Because it has to do with the molecular formula. So here's an example. This is the best way to really describe this formula mass that we're going to be calculating. We're given chloroform, which has the formula. We see there's 1 carbon here, and then there's 3 chlorines and 1 hydrogen, BCl3H. So we see we have 1 carbon, so we look at the periodic table, we get its atomic mass, 12.01 AMU. Okay, and there's 1 of it, so we have 1 times 12.01. Same for hydrogen, 1, only its mass is 1.008. And then we have 3 chlorines, so we have 3 times its atomic mass of 35.45, which is 106.35. We add everything up to get the molecular mass of this molecule, and that is 119.37 AMU. So here is another example. This is the aspirin molecule. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon. I know they're all written here, but may as well just kind of show you. Oxygens, it has 1, 2, 3, 4, and then hydrogens, it has 1, 2, 3, 4, 5, 6. So you can see the quantities, and then they're being multiplied by their atomic mass for whatever atom it is. We get the subtotals for each one, add them all up, and we get a molecular mass of aspirin of 180.15 AMUs. Here's one more example. I forgot to put the name of this. This is ibuprofen, aka Motrin. And it has the formula C13H18O2. So you've got 13 times molar mass or atomic mass of carbon, 18 times the atomic mass of hydrogen, and 2 times the atomic mass of oxygen. Add them all up, and you get 206.27 AMUs for the molecular mass of ibuprofen. Now, let's talk about it for ionic compounds. Ionic substances have discrete cations and anions that are combined in a ratio. So they're electrically neutral, if you remember from last chapter. but they do not exist as molecules. Okay, so the formula mass of an ionic compound is not its molecular mass. Okay, so we call it the formula mass. So it's the mass of the actual formula. So for instance, this is what sodium chloride actually looks like. It's not just little tiny Na and Cl's all by themselves. They actually form this cubic structure where you have the positive and negative charges alternating. Positive being sodium, negative being chlorine. So the formula mass, okay, is just from NaCl, 1 sodium to 1 chlorine. So 1 and 22.99 for sodium, and chlorine 1 times 35.45 atom up. So this is its formula mass. It is not a molecular mass. Here is another example. This guy is aluminum sulfate, and it has the formula of Al2SO4. So this has a polyatomic ion, and when you're doing these formula masses with polyatomics, you see that there's 3 SO4s, which that means that we have 3 sulfurs. You have to multiply it times their subscript, and then there's 12 oxygens, okay, because there's 3 SO4s. So do the element quantities, their masses, and it says molecular mass. That's the typo in the book. Formula mass, 342.14 AMUs. All right, and that brings us now to the mole, not the oddly cute animal. This is the chemistry mole, and it is a mount unit similar to things like a pear or a dozen or a gross, right? If I buy a dozen eggs, it's kind of easier to say, oh, I had to buy 3 dozen eggs than to say 36 eggs. I know, it's not that much different, but it's the same type of thing. It's used to represent a large number. So the definition of the mole is technically the number of atoms in a sample of pure carbon-12 weighing exactly 12 grams. But it is how we can link between mass and number of atoms, molecules, or ions in a sample. So it's actually been determined to be 6.02214179 times 10 to the 23rd. And this is called Avogadro's number, named after Amadeo Avogadro. We just round it. We don't need to do that many sig figs, so we round it to 6.022 times 10 to the 23rd. And this is equal to 1 mole. Okay? And it doesn't matter what it is. It could be a mole of hydrogen atoms. It could be a mole of water molecules. It could be a mole of people. It could be a mole of candy, a mole of donuts. Doesn't matter. It just all depends on what it's specified to be a mole of. Okay? Now, the masses of 1 mole are different because the elements are different. They have different numbers of protons and neutrons, giving them different masses. But the number of whatever it is, things in 1 mole is the same. So here's an example. Every sample you see here contains 1 mole of atoms, 6.022 times 10 to the 23rd atoms. Okay, so zinc, 1 mole of it weighs 65.4 grams, whereas a mole of carbon is 12 grams, a mole of magnesium is 24.3. So you can see the difference in the masses of these different compounds. You know, look down at lead, 1 mole weighs 207 grams. Pretty heavy, right? So this brings us to the molar mass of an element. And this is the mass in grams of 1 mole of whatever it is that you're looking at. And so the units of this are grams per mole. And this is actually numerically equivalent to AMUs. to the atomic or formula mass in AMUs. So we can say, you know, that one carbon atom has a mass of 12.01 AMUs, or a mole of carbon weighs 12.01 grams. As you see right here. So the atomic masses that you can get from the periodic table, you can also use as molar masses. And that goes the same for calculating the molar mass of a compound. You add everything up just like you did for formula masses. Here's some other examples of 1 mole of different compounds. Let's see, what do we have here? 1 octanol, mercury 2 iodide, methanol, and sulfur. So then here's some examples, some different elements, their average atomic mass, their molar mass, and the atoms per mole. Notice atoms per mole, it's all the same. It doesn't matter what it is you're looking at. If you have 1 mole of it, you have 6.022 times 10 to the 23rd. But then you can see the average atomic mass and the molar masses, same numbers, just different units. Number of molecules, single droplet of water is roughly 100 billion times greater than the number of people on Earth. Crazy, right? All right, so let's talk about some calculations using the mole. So we can use their relationships between formula mass, the mole, and Avogadro's number to really compute various quantities. So for instance, we use the mole, or we use mass as a way to count atoms or molecules, because we can then convert it to moles using molar mass. So let's look at example 3.3. We're told we want to know the estimated average requirement for dietary potassium is 4.7 grams, and we want to know what this is in moles. So we're just talking about potassium, okay? So we need to go from mass to moles, and we do that by using molar mass. So we look in the periodic table, we see the molar mass, or atomic mass of potassium is 39.10 grams per mole. So we could write that as saying 39.10 grams per 1 mole, but that's not how we need this to cancel out grams. So we can also write this, if we use it as a conversion factor, of 1 mole for every 39.10 grams. That's what we need, so that we end with moles and cancel out grams. And we get 0.12 moles of potassium. So here's another example. A liter of air contains 9.2 times 10 to the negative 4th moles of argon. What is the mass in a liter of air? So this time we're going from moles to mass. We're still going to use molar mass. We go look up in a periodic table and we see that argon has a molar mass of 39.95 grams per mole. And we want to cancel out moles, so this is written as the right way, a conversion factor to get rid of moles, end with grams, and we get 0.037 grams. So here's another example that we're going to work through. We're told here's copper wire, and it's composed of many, many atoms of copper. We want to know how many copper atoms are in 5 grams of copper wire. So to do this, we're going to start with our mass of copper atoms, which is 5 grams. And then we're going to go to moles of copper atoms, because we can't just go straight from mass of atoms to number of atoms. We need something in between. So we can go to moles, because then we know how to go from moles to number using Avogadro's number. And we can go from mass to moles using molar mass. So we're told we have 5 grams of copper. And when we look at the periodic table, we see that the molar mass of copper is equal to 63.55 grams per mole. Now we need to get rid of grams, which means we need those on the bottom of our conversion. So we have 63.55 grams. On top, we have 1 mole. We see grams of copper cancel out. And now we need to go from moles to number. And we're going to use Avogadro's number, which we know that there are 6.022 times 10 to the 23rd atoms per mole. And that's how we need it written, because we need to get rid of moles. So those need to be on the bottom. And 6.022 times 10 to the 23rd atoms go up top. And you punch this into your calculator and you should get 4.74 times 10 to the 22nd atom. That's a lot of atoms. And that's still not even a full mole. All right, here's another example. We're told our bodies synthesize protein from amino acids. One of these proteins is glycine, which has the molecular formula C2H5O2N. How many moles of glycine molecules are contained in 28.35 grams of glycine? So here we want to go from mass to moles, and we're given 28.35 grams of glycine, but we're also given the formula of it. So we can figure out its molar mass by calculating it. So we have 2 carbons. So we have 2 times 12.01. We have 5 hydrogens, 5 times 1.008. Get these from the periodic table. 2 oxygens, 2 times 16.00. And 1 nitrogen, 14.007. 4.2, 5.00, 32.00, and 14.007. Add everything up, take into account sig figs for decimals, and we get 75.07 grams per mole. Okay, so now we can go ahead and do our calculation. 28.35 grams. And we know there's 1 mole for every 75.07 grams. Grams cancel, we're left with moles. And we get 0.378 moles. Oh, and there it is again. All right, let's look at another example. We are told vitamin C is a covalent compound with the molecular formula C6H8O6. Recommended daily dietary allowance for kids is 1.42 times 10 to the negative 4th moles. What is the mass of this allowance in grams? And they were nice and actually told us the molar mass instead of making us do it ourselves. So we have moles. Oh, my book is pushing buttons. We have moles. We want grams. So we start with what we have. We have the molar mass, grams over moles. Moles cancel. We get 0.0250 grams of vitamin C. All right, now here's one more. A packet of an artificial sweetener contains 40 milligrams of saccharin, which has this structural formula. Kind of a cool formula or structure, isn't it? Given that it has a molar mass of 183.18 grams per mole, how many molecules are in a 40 milligram sample of saccharin? And they give you a lot of extra information. You should be able to go from milligrams to grams on your own. You should even potentially be able to calculate the molar mass on your own, but hey. But it wants to know, and then how many carbon atoms are in the same sample. So we're going to start by taking the grams of saccharin, use our molar mass to get moles of saccharin, use Avogadro's number to get number of molecules. Okay, so we had 40 milligrams, which was changed to grams. even though they told us, but just to kind of refresh your memory. We had 40.0 milligrams, 1 gram per 1,000 milligrams. Gives us 0.0 grams. And you need to do this because your molar mass is in grams, not in milligrams. Okay, so grams cancel, and then we go from use Avogadro's number to get us molecules. So then we're told that there's 1.31 times 10 to the 20th saccharide molecules in 40 milligrams. But then the last part is it wanted to know how many carbon atoms there are in this number of molecules. And when you look at the formula, you see that the C7. So that means there's 7 carbons for every 1 molecule. So we're going to take our number, multiply it times 7, and we get 9.17 times 10 to the 20th carbon atom. So make sure you're paying attention to what the question is actually asking you.